this kind of introduction to Helix. This is going to be a 3-hour session. We're going to break it up into 1-hour chunks with different presenters in each of those hours. As you can see, we're going to be recording each of those hours separately, and we can share those around afterwards. There's no obligation to go to all 3 hours. It's kind of up to you and your needs. Each hour is going to get kind of progressively more detailed. This first hour, Aadil over at NREL will be presenting and kind of providing a general overview and how Helix has been used. The second hour, Phil Top at Livermore will be presenting. He's he is the lead developer of the core Helix library, so he'll be getting into some of those details and about that. And then the third hour, I'll be presenting and talking about how to use Helix a little bit, as much as one can. We'll be looking at some actual example code that the Helix team has put together. So feel free to pick and choose however you feel like your needs would most be met. I guess with that, Aadil or Phil, is there anything else to say, or can we just get going?
No, I think welcome everyone. And if you know of other people who are interested in this, feel free to send them out. We're making this open to anybody who was interested.
Great. I'll begin then. Hi, my name is Aadil Latif. I've been working at NREL for about 6 years now. I wasn't part of the original Helix team, joined the Helix Plus team, which was the extension to the Helix project. And my job today is to give you an introduction to Helix, which is the hierarchical engine for large-scale infrastructure core simulation. My intention is to keep it fairly high level. I'm going to assume that most folks here do not have an understanding of what core simulation is. And with that in mind, I'm going to try and keep this fairly high level, and hopefully after the first hour, you'll have enough information that you'll be able to follow along, both Trevor and Phil for hour 2 and 3. I will stop in between slides, so if you have any questions, feel free to raise your hand, and we can try and answer those questions as I go along the presentation. All right, so as the power system is evolving, actually, camera as well. So as the power system is evolving, right, we've got increasing electrification. We've got electrification of vehicles. We've got electrification of fuels as well. So we're working towards hydrogen as a fuel source, which means we would need to produce hydrogen from electricity. We've got renewable energy sources integrated to the power system. We've got much more advanced controls integrated into the system that is controlling the different domains. And because of all of these integration between different subdomains, we require a lot of integrated analysis. So if we take a step back and we talk about the energy system is studied in multiple subdomains, right? The power system is not one piece that we study. We've got the transmission system, we've got the distribution system. The transmission system is where you generate and transport bulk energy. The distribution system is where the end consumers are connected, right? Folks like the individual houses, the buildings, the end consumption points of the electricity. So this is essentially the last leaf, the last piece of the grid that you're actually connected to. So even when you think of the power system, you've got multiple subdomains that are studied separately, right? And when you think of other pieces that actually interface with these subdomains, you've got controls and communication. Controls, when you want to change system states and generation set points, for example, would be one thing. You've got communication, but you need to be able to sense the state of the system, right? You need to be able to understand what the system state is to be able to react to contingencies, for example. So all of these are very different pieces that have been studied classically in separate subdomains. And then you've got interactions of these energy. It's not just one domain that can be studied separately. So when I talk about increasing electrification, I'm talking about the transportation system, the power, the gas. They're all subdomains within the energy system that are coupled together, right? And we'll talk about that in a minute. But the idea here is that all of these subdomains have been studied separately up until a decade ago, where we started to talk about co-simulation just because computational capabilities caught up with the ability for us to be able to run a co-simulation. So when I talk about these subdomains, we've got the transmission system. We've got both open source tools and commercial tools to study the transmission systems, right? We've got PSLF and PSSC as major vendors for modeling the transmission system studies. So if you go to any utility, large scale utility, you'll see that they'll be using one of these models, right? For the distribution side, you've got SIME, you've got Synergy, you've got Windmill. These are all commercial tools, and you've got OpenDSS tools like GridLabD and OpenDSS that are typically used by national labs or universities, right? Research institutes. Similarly, when you look at controls and communication, you've got a lot of different tools that exist that allow you to actually simulate a communication network. Tools like OMNET, OPNET++, OPNET, OMNET++, and NS3. And then for the transmission system, you've got additional tools like Beam, like Encord, that allow you to simulate, say the natural gas system or the transportation system. Now, and each of these tools are well trusted, right? For example, PSLF, the original code was written in the 1970s. Same is true for PSSC as well. So a lot of these tools have been developed over a very long period of time. They've been thoroughly tested, which means that the community really has a lot of trust in these tools. So the results that are simulated, right? And that is one key thing when we're talking about simulation, right? Given simulation is the abstraction of reality, we're trying to replicate what is happening in reality. We need to have surety in the results that are being generated from the simulation tools. And asking a vendor to switch a simulation tool is no easy task. So something so a vendor typically would continue to use a tool that he trusts, right? And now when I talk about this, there's been very large amounts of time and effort and investments also that have gone into development of these tools, right? And they're all silos of excellence, which means we need to be using them going forward. So how do we use them? While we also want to make sure that we start to incorporate the intricacies of the subdomains interacting with one another, right? Up until now, we've studied transmission system separately. We've studied the distribution system separately. Now, what we want to do is that, given this evolving nature of the power system, of the energy system in general, we want to be able to understand how, for example, a control on the power system would impact natural gas, or an outage on the natural gas would, say, impact the power system stability, right? So all of these things need to be considered now because of the increasing coupling between these multiple subdomains. And one of the ways you can do that is by actually doing a co-simulation. What co-simulation allows you to do is it actually acts kind of like a glueware. What it essentially allows you to do is communicate with different simulators that already exist and exchange information between those simulators, and essentially try and couple these subdomains together in a way that gives you a much richer simulation, right? So you can have both the transmission system modeled in full fidelity, you can have the complete distribution system modeled in full fidelity. You can see the interaction between these tools. You can exchange information as the simulation is running, and I'll talk about that in a minute. But you can actually exchange information between multiple subdomains, and as you do that, you're able to have a much richer understanding of the overall impact of a simulation, right? So you can simulate very rich scenarios without having to say either reduce the fidelity of your model. So that is typically what would happen if you're looking at the transmission system only simulation. What essentially happens there is you aggregate the distribution model. You've got represented as one single lump load. So you're not able to see what is inside the distribution model, right? You're aggregating all of that. You're reducing a lot of fidelity. You're simplifying models, making assumptions. With co-simulation, you don't have to do that. you can have very rich models communicating against through one another and have a much richer understanding of what the total network, what the total simulation is essentially going to look like. So what is Helix? Helix enables bringing together one or more existing tools, exchanging data as time advances. So as you're going through simulation time, as you move forward in time, you're able to exchange information across these simulators, and you're able to have a much tighter simulation with a lot richer features, right? So just to give you an understanding of what Helix is, all these, so Helix stands for Hierarchical Engine for Large-Scale Infrastructure Core Simulation. It was designed to be extremely scalable. One of the limitations we saw with earlier implementations of core simulation frameworks, and there exist quite a few besides Helix as well, was the scalability aspect. We wanted to build out an interface that would be able to scale from 2 to over a million federates. We've already seen in literature folks being able to simulate a million federates with Helix with ease. We wanted to build a platform that was a framework that was cross-platform, essentially that works on the HPC, which is the high performance computing capability. We wanted to make sure that it works in the cloud on individual workstations and laptops as well. We wanted it to be modular. So essentially, the idea here would be you should be able to mix and match between different simulation tools. And I'll get into that in a second. We wanted it to be minimally invasive, so a small code base that is independent but is able to couple things together. We do support a lot of popular languages. We support the Python interface. We've actually got 2 Python interfaces. I think Bill probably is going to talk about that in his next presentation. We've got an interface for C++ and C, which Helix is natively written in. We've got interfaces for Julia, MATLAB, Java, and then FMI, which is functional markup interface. This is open source, which means we can accommodate pull requests. So if you have any feature additions you want, we are very active. If you have issues with any piece, you can create an issue on our GitHub page. We would look into that. And it supports many different types of simulations. So time series simulation, dynamic simulation, and events as well. So discrete time events are also, Helix is capable of managing all of those different types of core simulations. We have a lot of other features that I would want to very quickly highlight as well. So we've got tight coupling. So when I talk about loose coupling and tight coupling, so loose coupling is essentially exchanging information between simulators each time simulation time step, and then moving forward in time. And tight coupling, when I talk about tight coupling, and what I'm meaning is that we're able to exchange information multiple times until convergence is reached across multiple simulators. And only then when the convergence is reached, we move forward to the next time step. We've worked on a web-based simulation monitoring tool. So it's easy to debug simulations when you've got just a handful of simulators as part of the core simulation federation, right? When you scale up to say 10, even 100 simulators, for example, understanding how your simulation is orchestrated, trying to debug things if things go wrong, it becomes challenging. So we have spent a lot of time and effort on developing the web-based interface that allows you to look at the simulations as they're progressing to help you with the debug process. You've got built-in units management. So for example, we've got management for voltage. So you can do unit conversion on the fly. You don't have to do that as part of your code base. So Helix is capable of converting between units, if that makes sense, of course, right? So for example, if kVA to kilowatt or voltage to kilovoltage, for example, is doable. You don't have to manually multiply or subtract by 1,000. We do support real-time mode as well, so wall clock time. So you can use Helix for, say, real-time simulations. So say you have like an Opal RT communicating with, say, an OpenDSS model or whatever. So you should be able to do that with Helix as well. And then one thing that has been a recent addition is the ability to create dynamic federations. And what that means is, as the simulation is running, you should be able to add new simulators to the core simulation. And that is a new feature that has been recently added. A lot more detail is available on our page. So helix.org is the website we maintain. And if you go to that website, you should be able to see a very thorough list, a very thorough documentation, and a very detailed description for all the features that exist. All right. On the right side, we have this diagram. But just wanted to showcase, we've integrated to a lot of tools we support. More than 25 different simulators have already been integrated into Helix. So the tags in blue are the ones we already have an interface for. For example, SIME, OpenDSS, GripLD, all have a Helix interface that we have. We've already integrated PSSE, DynGrid, InterPSS, Festive, all of these different tools for the transmission system have a Helix interface as well, right? And same is true for the comms control and additional tools that for buildings, for natural gas, for transportation, etc. Any questions up to this point? All right. So before I talk about core simulation, I just really wanted to spend a minute here and talk about what core simulation is, right? So when we're talking about different simulators coming together, what do we mean by that? So what is the responsibility of a core simulation framework? In my understanding, there are only two main responsibilities. One is message passing, and the other is time synchronization. When I'm talking about message passing, what I'm essentially talking about is this postal service example that has been given. We want to make sure, if imagine you've got simulator A, B, and C, you want to pass a message from simulator A to simulator C. Your framework should be capable of handling that, right? So the right federate gets the right simulator gets the information that is needed, right? And the second piece, and that is critical, is making sure that all simulators are time synchronized, right? Which means as you're moving through the simulation, all simulators are capable of maintaining that time. All of the simulators synchronize in time as well. This is no easy task. So a core simulation framework doesn't actually model anything. It's just a glueware that is able to interface with different simulators and allows you to do a core simulation, exchange information through the framework in a time synchronized manner, essentially. All right. So why core simulation? One of the biggest reasons for using core simulation is it makes it possible to reuse components, right? So if I have developed a generic, say, Helix interface for OpenDSS, I can make it be a part of many different use cases. I can make it be part of the real-time example I gave you, where we interface an OpenDSS with OpenRT, for example. I can make it be part of a T&D core simulation where we have PSSE coupled with OpenDSS, or even more than just two simulators, right? So reusability is one big aspect, whereas when we talk about coupling of simulators, essentially there is another concept where we directly couple two simulators together. Those implementations typically are not scalable, and every time you come up with a new use case, you have to redo the entire implementation. So one of the biggest advantages, in my opinion, of using a core simulation framework is the reusability aspect. So essentially, if you have an interface developed, which is a one-time effort for a particular simulator, you're able to reuse that same interface for multiple use cases. A framework allows you to makes it easier to add and remove things, right? So an example I gave you was transmission and distribution core simulation. You've got a transmission simulator and a distribution simulator talking to one another. Now, if you wanted to add, say, a control layer on top of it, how would you do that when you've got directly coupled simulators? It's very difficult to do. With a core simulation framework, it's very easy to add new federates to the federation, right? To have more simulators added to your use case in a sequential manner, right? And essentially make your core simulation more and more complex over time. So you can have layers for transportation. You can add a layer for you could add a federate for all of these different pieces that whatever your use case is. You can incrementally increase the complexity of the system without having to rewrite parts of your code. And that is one of the biggest advantages of using a core simulation framework. Extending on why using core simulation, right? Standing on shoulders of giants. So this is an example that my manager had. And one of the ideas here is this, right? We've spent like over 40, 50 years developing some of these tools. PSSE, PSLF, for example, they initially developed in the 70s. We've got 50 years, 50 years we've invested in these tools, right? Their industry really believes in them. They stand by them. So we want to be able to reuse some of these tools that have taken a long time and a lot of capital to develop. We don't want to be reinventing the wheel, right? We don't want to be developing an Uber tool that is able to model essentially every subdomain that I've talked about, say the natural gas, the power system, communication. It is also not very easy to do that, right? So if you think about the nature of these different tools, some of these have very different types of solvers embedded into them. And all these subdomains probably you won't be able to simulate all of these subdomains using a single solver, which is what a monolithic approach would be. Whereas if you try and reuse the tools that already exist with the solvers that are already embedded with them, it makes it easier to reach convergence and make sense of results, right? We've already talked about subdomain specific tools. They have been thoroughly vetted over years and years. They're trusted by stakeholders and they continue to improve, right? And then what our focus is essentially just developing the interface to these tools instead of reinventing the wheel, taking time and effort to try and build a tool that is able to model anything and everything within the energy system domain. What we essentially focus on is just developing the blueware, so essentially the Helix interfaces to these tools. And once we have that, we can co-simulate with any other tool that has a Helix interface enabled, right? Developed. This encourages modularity, so you're able to readily swap between or add models, right? So that's one thing we've already talked about. We already have a large list of tools that we have an interface for. So most tools that are the most commonly tools for each subdomain, we already have a Helix interface for. All right. Modular development and debugging. So that is one of the major advantages of using a core simulation framework. It enables model swapping. For example, if you have an OpenDSS model, right, and you want to swap it with another distribution model, say in Sine or Synergy, you should be able to do that very easily if you're using a core simulation framework like Helix. And if you're using a direct coupling, that becomes a very challenging proposition. Also, we've got very well-defined APIs, so multiple developers, you can simultaneously work on the problem, right? So if you've got 4 different simulators that need to be integrated, right? Given we're not doing this strong coupling, right? So we're not directly coupling tools together. We're just developing the Helix interface. That development can go in parallel, right? So each subdomain expert can develop the Helix interface for that simulator, right? The simulator they work with, which means that the development for multiple simulation tools can go in parallel, and then each subdomain expert would be able to actually correctly implement the Helix interface for these pieces. And it's easier when you do it this way, right? It's easier to do version control. It's easier to manage your code base as well in a much more efficient manner. So typically, what we've done previously as well is we start off by doing a dummy, developing just a dummy interface for a tool. we pass around fake information. Once we do that, we know that the information is exchanged, it works fine, the Helix interface works fine. We replace one of these tools with a real model, and eventually the second tool with a real model as well. And in that way, what we can do is methodically work our way towards a much more complex co-simulation, right? So we have we're able to, in this manner, we can isolate problems very quickly as well, right? So if there is an issue with the Helix interface for, say, this real model, once we go down this approach, we're able to isolate problems very quickly and try and figure out where, if any issue lies with the Helix interface, where does that lie, and move forward with that. So we have some capabilities that we can talk about. I think probably Phil is going to be much more Phil probably would cover some of these pieces. So I'm not going to spend some time any time here. All right. So when we talk about hierarchy, when we talk about Helix, one of the main differences between Helix and other co-simulation frameworks is the hierarchy piece, right? So hierarchical framework is something that differentiates Helix from other co-simulation frameworks like FMI, for example, right? And what I mean by that is depicted well in this diagram here. Here, what we have is different simulation instances of the same simulation engine. So OpenDSS is the simulation engine here. We've got each red dot here represented an instance of that simulator, right? So each instance is running a different model altogether, a different distribution model, right? What we can do in Helix, there is one master broker that is responsible for the entire federation. But one thing that sets apart Helix from other co-simulation frameworks is the ability to have sub-brokers. And what that means is that you can have sub-brokers where your simulators can connect to and exchange information. I won't delve too much deeper into this because we've got an hour that Phil is actually going to talk about this in much more detail. But the idea here is that you can build your co-simulation in a hierarchy, and what that enables you to do is have a co-simulation like this, where part of your co-simulation is running on the high performance computing national lab, in this case NREL, and the part of that co-simulation is actually running in the cloud itself, right? And then you can just connect your sub broker to the master broker, and your co-simulation is going to run just fine. We recently ran a use case where we had 6 different national labs participating in a co-simulation across all of continental US, and the co-simulation framework worked perfectly fine. We were able to converge, run the co-simulation without any issues. All right. Any questions up to this point, by the way? I'll stop here for a minute for any questions. All right, then I'll continue. All right, one final piece. So what is another benefit of using a co-simulation framework like Helix is performance and scalability, right? Scalability, we've already talked about. Helix was built to be scalable, to be able to co-simulate over 1 million federates, right? And each federate we assume to be a simulator. That might be a single equation, that might be the complete simulator altogether, right? It allows you to inherently parallelize, right? What I essentially mean by here is that all of these instances can run in parallel as we move forward in time. So as you move to the next time, each of these can run in parallel across multiple machines, across multiple processes, right? So we can parallelize this and scale this in a very easy manner. Co-simulation allows you to break up the larger problem into much smaller problems, right? So for example, a very large power flows problem. So say if you want to do a transmission and distribution co-simulation, instead of implementing the entire transmission within the distribution network or vice versa, You can have both of them implemented separately, and then you can break it down into multiple pieces and co-simulate, right? So the distribution can federates can co-simulate with the transmission federate, which is the bulk power side. It enables you to use a mixture of solver types. I've already alluded to this, but you've when you're talking about simulation tools, you've got many different types of simulation tools, right? Some of them might be discrete events, some of them might be continuous, right? Depending on the nature of the simulator. Think of an example of a discrete event type simulator would be communication, right? So communication simulators like Omnet++ are discrete event type simulators. Continuous time simulators would be something like PSSC, right? Where you have time evolution of equations if you're doing dynamic simulation. And you've got very different types of solvers solving these problems, right? So trying to implement both the communication and power system within the same framework would be very difficult problem to solve. So what co-simulation frameworks allow you to do is each subproblem that is well suited for a type of a solver is solved using that, right, within a simulator. And then all you do is exchange information in synchronized time. And that allows you to solve problems that are very that would be very difficult to solve using a single simulator, essentially, right, in a monolithic implementation. All right. So Helix does have two classes of data. So there is physical values, and by physical values we mean, say, water flowing through a pipe, right? So if we have two pipes that are connected, water flowing through one pipe and exiting and going into the other pipe, you would have some variables that are coupled, right? So these are physics-based values that are not going to change, right? So when if we take these two pipes apart and we want to co-simulate and model them individually now, and we want to co-simulate, we want to make sure that the boundary conditions where these two match, where these two were connected, those boundary conditions need to be matching, right? Same is true for power systems as well, right? When we're talking about power systems, we're talking about variables like voltage or power itself that is flowing, or current, right? At boundary conditions, when we're doing these co-simulations, these are physical values, and we want to make sure that these values match at those boundary conditions, right? So voltage, frequency, current in power system, water flow, for example, or flow in general in a gas would be something that would be variables of interest, would be described as physical data. In this very simple example, we've got a T&D simulation. All we're doing is the distribution system is passing voltage values at the feeder head, and the transmission system. The transmission system is passing voltage values, and the distribution system is passing the aggregate P and Q value. So the aggregate power that is flowing through the substation, essentially. So that is passed to the transmission side, right? As we try and increase the complexity of the co-simulation framework, of the co-simulation use case here, what we do here is we've added the market, a market federate here as well. So market would have things like Maillard load. It would have price signals as well, right? And in this use case, Maillard load values are going to be subscribed by the market. So market is going to take values from the distribution, figure out what the Maillard load is, and it's going to dispatch generation assets on the transmission network based on what the actual generation is and what the current load is. And of course, this mismatch between generation and demand is going to impact the prices, and that might impact the load itself as well, right? So as prices go very high, you might see load consumption going down and vice versa. What you can then also do is add controllers on top of this, right? And that is typically how the power system is operated. You've got controls, you've got sensing data that is coming from both transmission and distribution, so you know what the state of the system is, right? So tools like state estimation algorithms are used to estimate the system state of the system, the system-wide state. And then you've got controllers that are actually controlling and changing the behavior of your model, of your system. So you've in this case, we've added another federate here. And in this case, these are messages, right? So these are messages that are being so these are messages. These are not physical values because these are actually sensed and then communicated via a communication channel, right? That might be different types of there might exist multiple types of communication channels that exist. There also might exist different communications control signals, and control signals, of course, is not going to be. There is going to be some communication delay and some packet drop that might happen as communication signal is transported via whatever communication channel that exists, right? So the point I wanted to highlight here are there are some physical values. So in Helix does differentiate between them. So these would be voltage, frequency, current. These would be flow of water through a pipe, for example, right? Then there is message. So there is value. There is a value type, and then there is a message type. And the message type is things that are being sensed essentially, right? One thing I wanted to highlight also is that for message type data, so for example, a controller is sensing information and then passing and then communicate via communication channel. Helix does have some built-in capability to mimic, say, communication channels. We have something called filters that allows you to simulate delays in communication, that allows you to simulate random packet drops, so essentially loss of information as information is traveling through these communication channels. And you should be able to see the impact of both of these in the core simulation. So imagine in such a scenario where you're sensing some information, there is a delay before that information gets to the controller. The controller changes some set point that gets communicated back to the distribution a controller that is implemented on the distribution side. But there is a delay here as well, and that might impact what is expected and what is observed, right? And that is something you can simulate with Helix built-in capability as well. What Helix also allows you to do is you can actually interface with the explicitly with the communications federate, right? A communication simulator that can be something like Omnet++ or Spectre or an NS3 Opnet simulation tools of that kind. I would say these types of tools. So communication simulators are typically used to say check for vulnerabilities in most power system use cases. Use of a communication simulator is an overkill. So you can get away with using Helix filters for most use cases that you want to look into, say packet drop or delays in communication, right? Communication simulation tools are typically used for evaluating the performance of the communication protocols, essentially. So that is what the main job is. So vulnerability of communication protocols and things like that is something you look into. So if you're looking into cyber physical systems where you have a cyber layer and you want to see, for example, cyber vulnerability and things like that, you want to study, you would be use case where you would potentially use a dedicated communication simulator. So how has Helix been used? We've used Helix for a plethora of different efforts. The general areas of growth, and I'll talk about this in would be transmission and distribution. So we've got natural coupling between transmission and the distribution side, right? There is growing coupling between transmission and the grid with electrification of vehicles, with hopefully with more hydrogen vehicles being moving towards hydrogen vehicles for both mass transportation and for industrial uses. you would have a lot more interdependence between the grid and transportation. New controls are being added, smarter controls are being added to the grid, which means there is a lot of interaction between controls and grid. There is natural coupling between natural gas and grid, right? So, for example, natural gas power plants produce electricity, and then there are compressor stations within the natural gas network that require electricity to run. So these are natural coupling points between the natural gas domain and the power system domain. And to be able to understand the intricacies and the dependencies of one another, and to make sure that they're stable in terms of in certain contingencies, we need to be able to co-simulate these subdomains together. So all these different projects that we highlight here are essentially use cases where we see a lot of coupling altogether, where we foresee more coupling between subdomains in the future. Anomaly detection is another example where what we're able to do is co-simulate a very complex system. We introduce faults and see what that fault signature does. We record those simulations, right? And we use that for anomaly detection. So essentially, we want to be able to see if the simulation that looks is if the simulation if this is anomalous behavior or not, right? So we've got machine learning algorithms to detect that, but to be able to train that machine learning algorithm, we need a lot of data which is not publicly available. So we're able to create synthetic data that allows us to train neural network, for example. Is one use case that we've done as well. All right. I've already talked about this. So this was part of the Helix Plus effort, where we co-simulated the power system grid with the natural gas co-simulation. We partnered with NCORD for this effort. One of the nice things about this example was NCORD has developed a tool called Saint that is able to model both the natural gas system and the power system within the same framework, right? And this is nice because what we can do now is we can actually build out both the natural gas and the power system within the same tool, which is coupled together. And then we can separate those out and glue them together via Helix, and we can compare what the difference between simulation results is when we couple the two domains together monolithically versus when we use Helix to connect them together, right? And the results you see here show that the results were exactly the same in both cases. So if we had a monolithic implementation versus a Helix implementation, a Helix interface, a co-simulation where Helix was essentially the glueware connecting two simulators together, we ended up with the exact same simulation results. For more information on this, if you're interested, I would recommend reaching out to Brian Sergey. Another thing we wanted to highlight here was the realistic simulation for controls, right? When we're talking about simulations for controllers, controllers impact the actual grid, right? And we don't want to directly test new algorithms, new controllers on the grid itself. So simulation is one way of understanding what the impact of a controller on a grid is going to be, right? And when we do this, we want to be able to do this in as much fidelity as possible, just to be able to make sure that the impact of our controller on the grid is going to be well understood, well captured with the simulation we have. So Helix is, of course, a really nice framework that allows you to do that very easily as well, right? So we've got interfaces for a lot of these different simulation tools, and because of that, we're able to study the impact of new control algorithms on large-scale systems in a much easier manner than ever before. I think one final use case I just wanted to talk about was the hardware in loop ADMS testbed. In this use case, we had Helix interface OpenDSS with an OpenRT agent, which is a real-time simulator. And in this case, Helix was running in real-time mode essentially, right? So wall clock time. So Helix can do both wall clock time simulations as well as simulation time, essentially, right? Where you lock simulator times and make sure things are synchronized before you move forward in time. So Helix was able to do that as well. Yeah, if you have more questions on this, I can connect you with Jin Tan, who was leading this effort. And one final slide I have on use cases, and in this case, what we did was we took this San Francisco Bay Area. This is 14 million electrical nodes, I believe. So this is a very, very large model. We wanted to co-simulate with the mobility network model, which is Beam in this case. So Beam is one monolithic giant model that cannot be distributed. So we had this running in AWS. We had this running in RHPC, and we communicated but connected hundreds of instances of OpenDSS with Beam via Helix. And in this case, as I showed in the first slide as well, we ran across multiple machines, across multiple nodes, and we had hierarchy implemented that allowed us to scale to very, very large values. And in this case, very, 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 very large systems. So there are other use cases. One I've already talked about, generating data from machine learning. So we develop synthetic data to train our neural networks, right? Cybersecurity analysis, another thing we talk about. So if you have, if you want to test out a new communication protocol, right? You can use something like Omnet plus Opnet, some communication simulator as part of your core simulation framework. Lawrence Livermore and Hydro-Quebec did do a study for this as well. NREL is doing something very similar with Spectre, which is a in-house tool for core simulation, for communication simulation that has a Helix interface. We've done large-scale multi-site demos. I've talked about this as well, where we had like 6 labs participating in a core simulation across the entirety of continental US. We've done very, very complex systems, complex core simulation systems for transactive energy, where we had transmission, distribution, market controls, all of these different simulators being part of one core simulation use case. Another use case we did recently and finished was co-convergence. So when we're doing these simulations, one of the things we think of is, are we converging as simulation is moving forward, right? In most cases, it's easy. So most use cases where you have tree-like dependencies, fixed iteration method that is built into Helix works perfectly fine. There are some very weird use cases that you might want to use an external solver to solve. So we have an example on that as well that is now open source. And then North America resiliency model. This is a very large effort for the Department of Energy. I believe 7 or 8 different labs are part of this effort. And what we're trying to do here is model the entirety of energy system in the US down to distribution level. So essentially every single household at least for the power system use case. So in that use case, we have the complete model for the natural gas, for the comms, and for the power system. And we want to see what the impact of different contingencies is, say a wildfire or a tornado and things like that, right? So we want to be able to study the impact of these events and the impact of these events on the energy system in general, and that is what NORM essentially is about. So Helix CLI is something we've worked on as well. So when we talk about scaling co-simulation, right, we were talking about 1 million plus federates. It's not easy. Once you start to scale up to very large values, we want to make sure that it is still easy to run that or orchestrate that co-simulation, right? And one way to do that is to use the Helix CLI. And what that essentially requires you to do is just build out one JSON file, and you can have a one-click simulation run. And what this JSON file allows you to do is launch all the different federates all the different participating simulators in a synchronized manner. And once that is done, the Helix can take over and start to co-simulate, right? And make sure that everything is synchronized and information is being exchanged as what is described within this framework, right? We've also worked on the ability to record exchanges, right? One thing that we wanted to figure out, and that comes from the usability aspect. We've had a lot of exchanges with folks trying to figure out what are additional features that are required for Helix to make it more usable. And one of the things that was recommended was the ability to record exchanges and store it in a database for retrieval later on, right? So if you run into, for example, convergence issues, you want to figure out which federate was responsible for that. And that in this implementation allows you to do that very easily. We also have a web interface that allows you to monitor the simulation as it is moving forward. This is an example of that. But what that will essentially allow you to do is look at all the information that is being exchanged between the different simulators, what is being exchanged, and in that manner, you should be able to understand if things fail, where they're failing from. That makes your life a lot easier. One final piece that we've worked on for the last couple of years is standardizing the interfaces, right? I've talked about multiple subdomains, but what I haven't talked about is the different simulators that exist for a particular subdomain. So if we take an example of one subdomain, say the distribution network, right? We've got many different vendors, many different simulators exist. And all of these simulators work more or less in the same manner, but their interfaces might be very, very different, right? And it's up to the user to build out this Helix interface, right? And those Helix interfaces might not look very similar across the different simulators. So the standardized Helix interface was essentially an effort towards standardizing those interfaces. So we wanted to make sure that these interfaces for a particular subdomain are standardized, because one of the major advantages of standardizing those interfaces is the ability to swap between them. So if the information exchange is standardized, if the naming convention is standardized, right? So how we exchange information is standardized. What we can then do is something like, say you have a distribution model that exists in OpenDSS. If we have the same model implemented in SIMDEST, you should be able to swap between them without the user having to do and writing a single line of code, right? And that is what we've been moving towards. We wanted it to be such a friendly, user-friendly ecosystem where the user is able to just plug and play his model, his simulator, and be part of a larger use case without having to write a single line of code. And that is what we're moving towards. And to that end, we've done a white paper on this where we standardized, we tried to standardize the for the distribution system, the distribution subdomain, the transmission subdomain, and the natural gas subdomain. And hopefully we move towards standardizing other subdomains as well in the future. And as I said, the standardization implementation reduces complexity, right, and allows one-click analysis. So once you've got those standardized interfaces developed, it makes it easy to swap simulators also, not just models inside simulators, but simulators themselves, and be able to run simulation. So we do support a lot of, we do have a lot of support offerings. So if you want, you can go to helix.org. That is the website that is maintained for both documentation purposes. We do very extensive documentation for both the native C interface as well as the Python interface. The Python interface, I believe, has a separate API as well, which is the Pythonic API that probably Phil is going to get into a bit more. We have a user guide that is for beginners. We've got a developer's guide. If you want to extend the capabilities, you should look into that. We've got a very thorough API reference. So any methods calls within the API are very thoroughly documented. Configuration options and reference to those are available as well. We've got a very good example suite now as well, right? We start from very simple examples and we touch very complex examples like co-iteration and all of those pieces. We've got a YouTube channel as well that discusses various topics, and then we've got screencasts for Helix in action as well. We do have a GitHub channel, so if you have any question and for real-time chat with the Helix team, you can just join that GitHub channel and ask your question, and people are available there to answer your questions in close to real-time manner. And then also, if you've got a larger issue that you want addressed, we do have bi-weekly office hours for debugging purposes with the Helix code developers. So Phil probably would be there as well to answer any questions on a bi-weekly manner. And that is the end of my presentation. Any questions, guys?
I would like to thank you for this presentation. It was very informative. That's it.
Well, we're at the top of the hour. Let's take a few-minute break. Many of us, I'll stay online if there are any further questions. I don't know, Aadil, if you'll stick around or if you have another meeting to jump to, but let's start again at 10:05. And if you don't have anything to do, you can just hang out here with us.
Yeah, I'll stay here. If you have any questions, I'll be here for the next minutes to answer those.